Today we're going to be talking about analysis of welds using DesignLife. Before we start, let's just take a look at the agenda for today. We're going to look a little at the fatigue of welds, just a brief introduction, and then we're going to focus primarily on seam welds inside of DesignLife. And I will end up the session giving an overview of WholeLife, which is another weld analysis approach that we do have. And then we'll open up to questions. Okay. I am part of Princia. Princia is actually the software division of HBK. And under that umbrella, we have two major brands, nCode and ReliaSoft. nCode looks at predicting durability using physics. ReliaSoft looks at reliability using things like warranty or field failure data. So obviously we provide software, but we also provide training not only in terms of how to use the software products, but also in things like the fatigue theory, design for durability, design for reliability, just overall educational courses. In addition, Princia has a services group, one being a material test laboratory in Sheffield. We also have groups that will go off and do service projects developing enterprise-wide solutions using our tools and others, actually. If you look at the software portfolio for ReliaSoft and nCode, it's fairly diverse. Again, ReliaSoft's having products looking at reliability, things like Weibel and FMEA. On the nCode side, we have a series of products that do analysis on measured test data in the vibration fatigue. And what we're going to be focusing in today on is the DesignLife, which uses virtual results. Since we're talking about DesignLife, I just kind of give you an introduction for those who haven't seen it. Basically, it is a tool that does fatigue on virtual results. So results coming from FE analyses. And it has capability to standard stress life and strain life with all the corrections one would expect. But it also has a wide range of advanced features in terms of welds, crack growth, adhesive bonds, multi-axial techniques, thermomechanical composites. And all this information is available from most of the standard FE results packages. So we can go in and import results from any of these fields in terms of things like Nastran, ANSYS, Abacus, OptiStruct. And as a system, it's very configurable. It is in its own right a process. And so you could open up a process inside DesignLife and have it already configured for you to be basically drag and drop. But you can also go in and customize it to a very high degree. And so it has a lot of capability there. And then its major strength, and this is typical of CAE-based fatigue tools, is its ability to go in and synthesize stress histories your part will see. When we talk about fatigue, we're not talking about max stresses. We're talking about the entire load history that a part is going to see over its life. And DesignLife has a wide range of capability to kind of synthesize pieces of FE stress results into these histories. So it's an efficient solution. With that, let's get started into the fatigue of welds. And again, we'll start with just a real brief introduction to kind of categorize the challenges and techniques for looking at welds. I'm then going to talk primarily about seam welds today in DesignLife, both in terms of shell modeling and solid modeling, and the common areas as well as the differences. Again, I will talk about WholeLife, and then after the summary, we'll open up for questions. So when we look at welds, we see that their behavior in fatigue is drastically different than parent metal. There's several things that show up immediately that basically the welds have much lower fatigue strength than the metal that's been welded. And so hence they're going to be the locations we start to see fatigue failures. When we look at the behavior of them, we see that the reason for this is twofold. One, we have left a very difficult geometry in our part in terms of the weld. And it has extremely large stress concentration factors. It may even have cracks existing already at the weld toes or weld roots. The welding process may have left extremely high tensile residual stresses in these welds, and they complicate the behavior because there's such a high residual tensile stress. They tend to make every cycle that goes through the weld a damaging cycle. And then the material is very hard to characterize because we've laid down a bead of weld metal. The welding process has taken the parent metal adjacent to that and has transformed it into what we call a heat affected zone, but the properties now are drastically different than the parent metal. As I mentioned, when we look at welds, the fatigue behavior is much lower in strength than the metals being welded. And you can see that onto the right where we have some representative stress life curves. The top curve in green would be representative of a tensile specimen where I have pure material and I've gone off and tested it. As I take that material and basically build a part of it and start to build in certain stress risers, we expect to see the behavior change some, and that's what the blue curve is. The blue curve represents part with some stress risers. The red curve is talking about a weld that we see at the bottom here, and actually that weld happens not even be load carrying. It's just a non-load carrying weld, but just the weld being there drastically changes not only the strength, you see that the strength is much lower than the parent metal, it also changes the behavior. You know that the slopes are much steeper. That slope is very indicative of crack growth. Basically, weld fatigue is a crack growth process. With that, you'll see that we have a variety of approaches for trying to go off and life apart due to weld fatigue. And the first one to come up would be fracture mechanics, because basically weld fatigue is a crack growth process. Problem with fracture mechanics, it's very much a point-wise solution. There's a lot of information that has to go in about the start point for the crack in terms of crack size, crack shape, directions, and they tend to drive the entire answer. So one, it's not something that's easily fit into an FE solution, and two, it's relatively laborious. And so we tend not to focus in on crack growth in most cases. There's another approach to the left called local stress. And here we actually, in our FE model the weld in reasonable detail, either in the global model or maybe as a breakout model that receives things such as displacements or loads from the global model. It has certain advantages in the fact that it starts to characterize more of the weld geometry. And so it can look at, a bit at things like weld quality. But on the downside, if this approach is put directly into the global model, the mesh density is such that you really can't analyze anything real. You know, it's just the refinement that has to go in and capture the weld behavior. Basically, it's going to just make it unusable. In terms of breakout models, they are much more efficient, but typically the ones I've seen have all been very much plane strain. Think of like a cross-section cut through the weld and looking at the weld in 2D. And so It's very powerful if I have a continuous weld, but typically where we see welds, weld issues is at weld terminations, and these don't really handle that all that well. So we're left with the final solution typically is a structural stress solution. And all a structural stress is a way to get a nominal stress out of my part, either realistically on our physical part with things like strain gauges or virtually on an FE model. But it's a way to recover a stress that may not be the actual stress at the fact it won't be the actual stress at the weld toe or weld root, but it's a stress that's very repeatable and can be used as a damage measure. And we're going to see that in the next slide. The last thing we have is a technique called WholeLife. It's relatively new. We introduced it about 2 years ago, and it is an approach that starts to marry fracture mechanics in an FE model. So I'll finish up talking a little bit about the WholeLife approach. So when we talk about structural stresses, they are a technique for us to recover stresses that we could use in a damage calculation, but have certain properties. One, it's virtually impossible to get the actual stresses in the weld. Like I said, the weld geometry is extremely complex. There may even be existing cracks in there. So the actual calculation of the stress in the weld, measurement or physical in an FE solution, is pretty much impossible. A structural stress is looking at, in essence, the load going into the weld. That's really what it's. So here we say that it's the stress near the weld or basically extrapolated up to the weld. But what we're trying to characterize is a normalized load at the weld failure location. And we can do this in the test environment with things like strain gauges near the weld or maybe in front of the weld and extrapolating up. In terms of finite element models, we have a variety of approaches to get structural stresses as well. And we'll see two of them today that we're using. But the goal here is to get a stress that's repeatable, is not that mesh sensitive, and I can go in and use that to characterize my fatigue behavior. These are nothing new. If you go off and look at almost any weld design code that you're familiar with, British Weld Standard, the ASME Boiler Code, IIW, the Euro Code, they all utilize structural stresses in one form or another to characterize the loads going into the welds. And hence, when we talk about DesignLife and our Seamwelds, we're doing exactly the same thing. With that said, let's kind of introduce Seamwelds. Seamwelds are nothing new to DesignLife or to the nCode products. A version of this has been in our products for close to 20 years. And obviously, over that time, it has evolved. The approaches that we have today are available both for shell and solid models. In many cases, one or the other is a far better representation of our global structure. Both of them have attributes that they require minimal meshing to define the welds. So that's one of the goals here, is to make it such that it's lightweight that I can put it into a global model. They both are using these structural stress approaches to reduce the impact of the FE model mesh on the results. And probably as important as anything is they both support a wide range of loading. Again, in terms of fatigue, we're trying to characterize loads on our part over its entire life to prescribe fatigue behavior. And so we have a variety of approaches, both in the time domain that can go off and look at things as simple as constant amplitude loads, but transient loads, loads that are brought in from a computer from measured force histories and superimposed. There's also the ability to look at this instead of the time domain in the frequency domain. So we can go in and bring in loads into the Seamwelds that are things like power spectral density or swept sign signals. And then finally, those individual types of loading can be combined into what we call a duty cycle that would go in and characterize a complex set of different environments a part would see over its life. So these are all available that can be used with our Seamweld approaches. And then finally, as I mentioned, Seamweld has been in software for many, many years. And over time, we have basically brought in a variety of enhancements and options to make it more powerful. 2 releases ago, we basically created 2 new glyphs in our palette that are focused at looking at shell and solid seam weld and have been configured with all our present best practices. So things that we've brought in to make life easier or make it more accurate are now basically selected in these glyphs. And so there's one for shell that's almost drag and drop. I go in, identify the shells, and it's using our shell approach with all our recommended procedures. The same thing for solids. In terms of seam welds and shell models, we have a system that is relatively easy to use. The mesh requirements are nothing more than I have an element, a shell element, that is the connector between my 2 parts being welded. Hence, it's the weld. And the locations that we're going to go and analyze are based off of those weld elements. They're not the weld elements themselves, but we use the weld elements to identify the actual physical locations we're going to calculate for fatigue life, as well as which surface of the shell is important. And again, we're using structural stresses, in this case, from forces and moments, to allow us to get an accurate measure of nominal stress going into the weld and be relatively insensitive to the mesh. In addition, it's looking at multiple sets of forces. So we're looking at normal forces and shear forces in this calculation, and that allows us to go off and use a variety of different stress quantities in our calculation, whatever tends to make the most sense for the loading conditions we're in. The actual meshing is relatively simple. All we're doing is connecting our 2 parts that are going to be welded together with a shell element that is the weld. And the mesh requirements are twofold. One, we'd like to have the shell element connect our parts where the weld toe or weld root's going to be. So basically, they connect to our parent metal where the weld toe is going to exist. And secondly, they're put into a separate group such that I can just point to all the elements that represent the weld as a group, identify that to DesignLife, and then DesignLife will go off and actually find all the attached elements and appropriate nodes for those. The last consideration is that we'd like to have the normal for these weld elements be pointing outwards towards the welder. The reason for this is we're going to go in and actually look at the weld configurations and decide where we should do the analysis on which surface of shells. And we need that information such that we understand how the shells are oriented that attach to these welds. And again, these configurations, whether a single element, 2 element configuration for welds, today are very easy to create. Automatic meshers such as ANSA, ANSYS Workbench, HyperMesh can go in and build these meshes automatically for you with all the requirements that we're asking for. One thing we do with the welds historically is we've broken them into different configurations, and I have 2 of them here. There's several, but the 2 major ones are fillet and overlap. A fillet is basically 2 plates that are perpendicular to one another, welded. The overlap are 2 plates that are parallel. The reason we go off and look at these different configurations is because the failures in the welds change as we go from one configuration to the other. You can see down at the bottom on the left-hand side, we have a failure in the vertical plate at the weld toe on the right-hand side of the plate. And that's because there's a geometric discontinuity at that weld toe. If I take that plate and basically, instead of being perpendicular, it's parallel, it still has the same topology as the previous fillet weld. But if we look at the previous failure location on the overlap, it's no longer a stress discontinuity. It's basically a relatively smooth connection. The failure now has moved to the other side of the shell and is now at the root, cracking up through the plate. So we need to account for these different configurations to allow us to be intelligent and find the right location to do our stress calculations. One thing that was added probably 3 releases ago is a new configuration called Combined Fillet and Overlap. Previously, a user was required to go off and decide which of his welds were fillet, which were overlap. With this new configuration, DesignLife does it automatically. We just put all the welds that we have into this configuration, combined fillet and overlap. DesignLife looks at the geometry of each weld and basically measures the angles between the weld and the parent metal and decides whether it's going to be a fillet weld, be an overlap weld, or be somewhere in between where it'll actually do both calculations. It then uses that information along with the weld elements to go in, identify all the parent metal elements that are touching the weld toe or weld root and classify them. The blue here being fillet welds, where they're primarily perpendicular to one another. The green being overlap, where they're almost parallel. And then you'll see that the red sections in here are in that transition region where they weren't exactly overlap or fillet. So we're doing both calculations. But we automatically go off and find the proper locations to do these calculations on. The other thing that's going on is how we calculate stresses. And again, this comes back to this whole concept of structural stresses. Structural stresses allow us to go in and calculate this damage measure that is relatively independent of the mesh. And this is an awful wordy slide, but just take a look at the picture here where we have green elements that represent the welds. And we can see we have 2 sets of parent metal attached to it. We'll focus in on the parent metal at the bottom. So we have these elements here that are touching the weld toes of our weld elements. What the force and moment structural stress does is it goes off, looks at the weld elements, finds the attached elements, then goes in and collects all the nodes shared by these 2 elements, and then grabs the forces and moments at the nodes from the parent metal elements, from basically the attached elements. So those forces and moments represent the forces and moments going into the actual weld. And from those forces and moments, we go in, transform them such they're in the edge coordinate system. We basically normalize them, turn them from point forces and moments into line forces and moments, and use those line forces and moments to calculate the structural stresses. The structural stress is a combination of basically a tension and a bending on it, and it's actually done in 2 reference systems. The first one is done with stresses that are normal to the toe and bending moments that are about that toe. The other is a set of stresses that are shear stresses between the 2 elements, and then a bending moment about that as well. And so these 2 sets of stress components go into our calculation, and they allow us to go in and use a wide variety of stress measures, whether it be toe normal, whether it be critical plane. And again, one advantage of the force and moment approach is it's applicable to almost every analysis package out there: ANSYS, Abacus, Nastran, OptiStruct. The reason that we do all this work is that these structural stresses are pretty much independent of the mesh. What I have here is a specimen. There are two rectangular tubes welded together by that purple line of weld that you see. And what we're looking at here is the stress normal to the weld along the weld toe of the weld and the blue box section that's horizontal. And these three models have a large difference in mesh density. Up at the upper left-hand corner, I have extremely fine mesh around the weld. If we go down to the upper right-hand corner, we have a very coarse model. So I have a very large difference in mesh density. But if we look at the stresses calculated from the forces and moments, they basically are virtually identical across these three different models. So again, I can go off and just use this approach directly, not have to worry about following detailed mesh guidelines to get this information. Then, as I said, what we have is a glyph that is set up to do exactly this. In fact, actually, let me go in and bring up a model. So what I've done is open a flow that's set up to do shell seam weld. And I'm going to go in and grab a model from here that should be recognizable because it was the model that I used in my first slide for the shells. And I'm going to identify the parts that are in there. So basically I have three components: the horizontal tube, the vertical tube, and the weld elements themselves. And again, these weld elements are a single element going down, connecting the two tubes together. And all I need to do is identify this group of elements to the program. And to do that, I'm going to actually use DesignLife to find just the displayed elements. Inside the seam weld, I'm doing a constant amplitude loading. I am pointing to a steel weld curve. And literally, it is nothing more than going in, having identified the welds, going off and running the calculation. Typically for seam welds, we would have a generic material applied, one for aluminum, one for steel. The only thing would go in and typically change would be the load provider. In this case, I use constant amplitude, but this could have been measured load histories. It could have been a transient solution. It could have been in the spectral domain as well with things like PSDs. And what we get out of this are a variety of results. The first thing I have plotted here is actually the configurations that were selected automatically by DesignLife. And so I have here, the blue represents the overlap welds, the green, the blue represents the fillet welds, the green, the overlap welds, and the red is the transition elements in between. But what comes out of this, more importantly, is information, things like life in terms of number of cycles to failure. I can go off and interrogate the locations that the welds were solved at. And not surprising that every location around this perimeter here are toes. So there are procedures inside DesignLife that very simply allow you to go off, grab the shell seam weld, and use it directly with all our prescribed corrections. We have this facility in shells. We also have this facility in solids. And again, same basic guiding procedures. In solids, we have two ways to represent the welds. One could be a group of welds, and that's what I'm going to show you in terms of the rest of the slides, where we identify the welds the same way we do in shells. I have a group of elements that have been highlighted. We have a second approach we call weld configuration file, and there are macros inside of like Hypermesh, ANSYS Workbench, Abacus CAE to allow you to go in, pick the geometry on these models, and output it's basically a text file that describes locations where I want to do the analysis and basically the direction the weld path is going to be in. Both of these go in and focus at looking at our weld here. And if I were to blow up on this, what we would see is those elements end up being identified, locations along those welds being identified, and these represent individual calculation points along the weld toes, weld roots that specify a location and a path the crack is going to grow. We're going to focus in on the new configuration approach that's inside of DesignLife that can build this path automatically just by pointing to the element sets that are the welds. These all basically use a structural stress, but it's going to be a different structural stress approach than the shells to make it easier to mesh in solids. Again, the meshing is pretty straightforward. You can be a matte mesh, you can be a free mesh, you can be hexes, tetras. And in general, this approach isn't tied to any particular node or element configuration. These are all basically just points on the part geometry, and it's independent of the actual mesh that's been put there. And so we're going to go off and look at the structural stress recovery approach here, which is through thickness integration. And again, compare it to the benefits we see coming out of the nodal force and moment structural stress in shells. The capability that was added a year ago in DesignLife is called the solid weld auto mode. But basically what it is today we have the ability, if we've grouped our weld elements into a separate group, property group, material group, element set, all we need to do for DesignLife is to point to that group of elements. And now DesignLife is going to go off automatically, interrogate those elements, find attachments to the parent metal, and any place that they attach with only one edge of the weld is fundamentally a stress discontinuity where the weld could crack. And so we'll automatically find like this toe line here and generate a series of locations and paths along that toe to do calculations on. The same thing for the upper toe connected to the red elements. When we get down to the root section, there's even more logic going in and looking at multiple paths that we could see failures occur. And so there's actually an additional parameter that goes with this where we can control. We're now looking at the root section here, and we can control how many paths basically come out of this root section across our weld geometry. And so let's go down to the bottom one here for 3. And so basically the starting point I would use would be 3. 3 would go in and give me a weld failure location that's going forward from the weld root and looking at peeling the weld off of the vertical plate. There's also a path going upward from the root that's looking at peeling the weld off of the one before was peeling off the horizontal plate. This one's peeling off the vertical plate. And there's a third one going in down through the vertical plate that's root cracking through the parent metal on that horizontal plate. We can go in and request additional paths. And what these allow us to do is to now start putting paths through the weld throat itself. So using the solid welds, we're able to go off and analyze not only the classic failures we'd expect to see in the shells, toe or root failures, we can start to go off and accurately start calculating throat failures from this as well. And again, this is nothing more than setting a property and how many, the default inside of the Glyph is 5. And so the default setting that you would use without going off and changing it, it's looking at trying to pick up the dominant modes, failure, toe, and root, as well as a throat failure in the part. The reason we go to this approach here is this technique that we use is relatively free of where the node and element arrangement is. As long as I have 3 elements through the thickness, I can go off and use this approach to get stresses. It's called through thickness integration. And so we basically find a location where we're going to calculate a stress, and we have a path down through a particular part. And what DesignLife does is it walks through the mesh along that path and calculates the actual stresses in those elements at those locations. So it's walked down through here. It doesn't have to be a path of nodes or a uniform path of elements. It's just an arbitrary mesh, but we calculate the stresses along this path. Once we have the actual stress for that path, we linearize it. So now what we have is a stress measure at our toe without the toe being there. This would be the nominal stress. And because we've actually got the stress profile through the thickness, we also understand what loading caused that stress, which is actually important in these approaches. We haven't got into this. If you're interested, there's previous webinars on Seamwelds on our website, and they'll go into a several slide description of taking structural stresses and using them for fatigue. But one of the things we have to identify is what loading causes the stress so we can make the appropriate corrections. And this gives us the ability to do that without any real benefit, major tasks on meshing. And then the reason we do this is the fact that I can go in and take, this is just a simple cruciform specimen. Their vertical members are being loaded, pulled in tension, and they are welded to a horizontal plate here with partial penetration welds. And I have the same geometry, same loading model with 4 different configurations, a very coarse hex 8 model, a finer TET 10, really fine TET 10, and a hex 20 model. And so I'm going anywhere from 6,000 elements, linear elements, to over 400,000 quadratic elements. If I were to look at the stresses coming out of the FE program from that, I see that I have max stress levels across the model anywhere from 12 to 25. That is a huge range in stress when you look at fatigue. If I go in and look at these structural stresses, all of a sudden, it's now giving me a fairly consistent measure across these different models. In the model with 6,000 elements, I was at 9.5. In the model with 400,000 elements, I'm at 10.5. So even though these meshes are completely different styles of elements, different levels of refinement, this structural stress is a relatively consistent way to use as a damage measure to drive that. And again, there's a new glyph inside of DesignLife that's plug and play for solids. I basically drag in my solid model, identify the group of elements that are the welds, and it will automatically go off, find every attached toe, root, and calculate paths through them automatically. And again, both the shells and solids allow you to go in and bring a wide range of loading. So it can be very complex multi-axial loading going into these to do the calculations. Finally, just quickly on WholeLife. So the Seamweld technique is using structural stresses directly as our damage measure. And they're using very simple SN curves based on those structural stresses. What we have is a new approach for doing welds inside DesignLife. This is based on a approach basically described by Greg Glinka, and it combines initiation and propagation into a single calculation. And we've inherited that and put it into a final element solution. The reason we've done this is this gives us a more accurate way to describe the weld fatigue if we know more things about the weld. So again, you don't get anything free. I have to understand more about the weld geometry, stress states, and material properties, but I can go off and do a much more refined calculation. It's using the standard global models we use for Seamweld, either shell or solid. It has the ability to go off and look at individual designs of welds and bring in information such as their stress profiles to describe their behavior exactly. We can look at a variety of failure modes. It's a relatively efficient calculation because we're using Seamweld as a filter to identify just critical locations to do this calculation on. It supports multi-axial loading, so it's a standard final solution. Types of loads you put on just a global model can be used in this calculation automatically. And we actually have the ability to import either measured or predicted residual stresses. The crack growth approach itself is rather unique. Dr. Glinka's thought on crack growth is what it actually is just successive failures due to crack initiation. And so each grain that the crack comes up and hits to is now going to be loaded and eventually will initiate a crack, which basically causes that grain to be structurally unsound. With the concept that we have basically lost the structural integrity of a grain at the tip of the crack, his assumption is the crack isn't a sharp point. It is actually a blunt notch with the radius of the diameter of the grain. The moment I make that assumption, I now have the ability to have a finite radius crack tip. I can predict the stresses in front, around, and behind that crack tip in great detail. It's no longer a stress discontinuity. In addition, once I have those actual stresses, I have the ability to go off and account for plasticity, both the loading and unloading, and look at things like residual compressive stresses due to plasticity in front and behind the crack. So it gives me a lot of capability of going in and doing this crack growth without any sort of assumptions in crack closure. I can model that directly. The other key aspect of this is the starting point is basically predetermined by the calculation, is this radius of the grain. And so that's our starting point. So it eliminates a lot of the unknowns about what my starting crack size is. It literally is based on the microstructure. And what we've done is taken this basic crack growth approach and have integrated it directly into a final solution. So what I have is my standard final model that we see here with basically arbitrary loading going in, multiple channels of loads, multi-axial loading. And the first step of this is a Seamweld calculation using either a shell mesh and the shell Seamwelds or the solid Seamwelds. And then what we do at the critical locations identified by Seamweld, we'll go in and we'll increase the information that we know about the part. And what that information actually is very detailed profiles of the stresses going through basically the crack path. This crack growth approach uses stress intensity functions, which basically are the way that we drive the crack growth. But the stress intensities that are used here are created by something called the uniform weight function. And what the uniform weight function does is calculate the stress intensity by knowing what the stress profile is through the part without the crack being there. So these detailed stress profiles give us the ability to go in and allow WholeLife to calculate the stress intensities by just knowing the stresses before the crack was there. You'll see that we have two loading modes here. And again, this follows back to the things that we were doing with Seamweld, in that we need to understand what causes this peak stresses, because they have a different influence on fatigue. So we basically separate these into two different loading modes, bending and membrane. They're independent of how many load cases I bring in. I can go in and have multiple load cases, and automatically DesignLife will basically consolidate them into these two behaviors, membrane and bending. In addition to the profiles of stress due to the loading, you could also bring in a profile of stress that is the residual stress from the welding process, either measured or predicted. And these will be incorporated along with the stresses from the operational loads as part of the crack growth behavior. And then finally, nothing comes for free. What we do need is more detailed material information. So we need to have crack growth behavior to drive this crack growth procedure. We also need to have the stress strain behavior from something like StrainLife, so we can go off and do the plasticity calculations that are happening, such that we can calculate the residual stresses left from the cycling in front of the crack tip and behind the crack tip. Now, we've brought this into DesignLife not to replace Seamweld. The concept here, the Seamweld approach is very simple, requires very little information, can use relatively generic curves to describe this. But no matter how good we are with basically condensing all this test data down, and we do have a very tight condensation of data here, if you start looking at it in a horizontal axis, the life axis, you'll see that these curves are based on a scatter of data. It's almost a decade wide, which means when we go to use this, we actually have to be relatively conservative. So we're designing for the worst case welds when we do this. That's a significant penalty if I have a welding process that I can control the weld quality and produce better welds. So if I can consistently build welds out on this upper section, I should be able to design to that. WholeLife gives me the ability to go in, bring in more information that I know about the welds in terms of these stress profiles and more in the weld geometry, and use that in my calculations. What we see on the right-hand graph, this graph here is a comparison chart. The horizontal axis is the life from test specimens. The vertical axis is life predicted by, in this case, Seamweld and WholeLife. The diagonal you see in black is a perfect fit. The test and prediction match exactly. The two other curves represent a factor of 2 scatter from that difference from test and prediction. Green being prediction is conservative, red being the prediction is unconservative. And you see all these blue, basically diamonds, are WholeLife predictions, and they all fit within that factor 2 scatter band. Down below, I've taken the same information and run Seamweld, our standard Seamweld approach, in this case in solids, and you'll see that they are very conservative, but they are going to force you to go in and make decisions on adding weight, reducing loads to pass. So the key here is that the Seamwelds give me a very good prediction when I'm looking at welds I don't have a good handle on their quality. The more I know about a weld, the more precise I can be with the predictions. And that's what WholeLife gives me. So it's in addition to the Seamwelds. Okay. So if I did this right, what I hope to talk about today was the fact that welds are usually the source of our fatigue failures. If we have welds in there, they're where we're going to see fatigue failures. Structural stresses are an ideal way for us to get a damage parameter to describe and a particular Seamweld approach. So they give me a reliable way to measure loads going into my weld. And again, in terms of an FE mesh, they give me the ability to go in and use a fairly wide range of meshing and still get the same structural stresses out. We have inside DesignLife approaches for this, both in shells and solids. The Seamweld approaches inside DesignLife basically allow us to use any of the load providers that we have in DesignLife, both time-based and frequency-based. And in addition, the WholeLife provides me a way that I can go in and take Seamwelds as a starting point and then add more refinement to the solution to get a better prediction. So if I know more about my weld, I can go in and leverage that to get a more precise prediction on life.